The law of conservation of energy states that energy can only change forms and that the total amount of energy must always remain constant. Today, we will test this law of the conservation of energy by evaluating whether the amount of energy at the beginning of a drop will indeed be transformed into kinetic energy by the end of the drop. Let's take a look at our procedure. We will drop a small white cylinder through vertical tubes of various heights. Because the white cylinder will be raised to a different height for each set of trials, it will begin with a greater and greater gravitational potential energy.
Here are our tubes. Short, longer, longer still. Ooh, almost, actually is taller than me. Much taller than me. Ooh, so tall I can't really even reach the top. This one is definitely taller. And finally, I'm going to need a ladder to reach the top to drop the tubes. I just want to show how we have to hold this. So I'm going to show this is incorrect. This is incorrect. We have to hold them right at the junction and let it go. I'm going to take a look at the equipment. Each setup consists of a tube of varying length and a holder for the photogate. And then the photogate is connected to the LabQuest. So you can see right there that the LabQuest currently reads unblocked. So it's an instrument that's going to read the velocity for us of a tube that will be dropped through the larger tube.
Let's take a look at our data sheet. Our data sheet is on page 224, and there are several things to point out. First, in the height column, the heights of our tubes are listed for us, except we need to modify two of them. The tube that was 0.615 meters needs to change to 0.625 meters, and the tube that was 1.08 needs to change to 1.15. From those heights, using those heights, and the mass of the cylinder, which is 0.04 kilograms, you are going to be calculating the energy, the initial energy that we start off with as we lift our cylinder to each of those heights. So we'll use the gravitational potential energy expression, which is mass times little g times height. So when we put in our values, we'll have 0.4 kilograms for the mass, 9.8 newtons per kilogram for little g. We don't have to worry about the sign. Energy is not going to have a sign, so we'll just use it as 9.8. And then the heights will be each of these heights. So you'll calculate the starting potential energy of the small cylinder that we lift. Then that cylinder is going to fall through each tube. We will run each experiment 4 times. We'll have 4 trials for each tube. So they're listed as teams because that's how we would be running them if we were at school. So each of those will be our 4 trials. We will not have 8 trials, so none of those columns will be filled in. Then from those 4 trials for each tube, you will then calculate the average velocity. So this column here will be where you will record the average velocity. And finally, using our average velocities and the mass of our white cylinder, we're going to calculate our kinetic energy, which of course the expression is 1/2 mv squared. So we'll have 1/2 times 0.04 kilograms times each of the average velocities. And we'll square that, and that will be our kinetic energy measured in joules. Make sure to use the average velocity when you calculate your kinetic energies. And then finally, we'll be graphing. And what we want to look for is a relationship between the gravitational potential energy, which is on the left-hand side in the gray column, and the kinetic energy, which is on the right-hand side in the gray column. So those are the two columns that we'll use to make our graph. We're going to start with the shortest tube, tube number 1. It is 0.305 meters. Run number 1. The velocity is 2.743. Run number 2. The velocity is 2.808. Run number 3, 2.818. And finally, tube number 4, 2.792. That completes the first set. Tube number 2, the length of tube number 2 is 0.445 meters. Run 1. Velocity is 3.253. Run 2. The velocity is 3.262. Run 4. The velocity is 3.257. This is run 4. The velocity is 3.249. That completes set number 2. Tube number 3, the length of tube number 3 is 0.625 meters. Run 1. The velocity is 3.727. Run 2. The velocity is 3.739. Run 3. The velocity is 3.763. And run 4. Velocity is 3.739. This is tube number 4. The length of tube number 4 is 0.76 meters. Run 1. The velocity is 4.014. Run 2. The velocity is 4.102. Run 3.
Velocity is 4.102. Run 4. .075. Tube number 5. Its length is 0.905 meters. Run number 1. Run number 1. The velocity is 4.332. Run number 2. Velocity is 4.357. Run number 3. Velocity is 4.334. And run number 4. Is 4.333. All right, we're up to set number 6. The length of the 6th tube is 1.15 meters. 1.15 meters. Run number 1. The velocity is 4.832.
Okay.
Run number 2. The velocity is 4.846. Run number 3. .845. That was run number 4. Velocity is 4.852. We are up to tube number 7. It is 1.20 meters. Run 1. The velocity is 4.999. Run 2. The velocity is 5.029. Run 3. Velocity is 5.006. The velocity is 5.033. We are up to tube number 8. This will be our last set. Run 1. Oops, sorry. The length of this tube is 1.36 meters. Run 1. The velocity is 5.299. Run number 2. The velocity is 5.345. Run number 3. The velocity is 5.308. Run number 4, our last run. The velocity is 5.259.
So let's double check your data, making sure you got all the data values. There are a lot here. If you need to double check any, you'll need to stop the video. Recall what you're going to do now is to use our expression for gravitational potential energy, MGH, and calculate the potential energy of our white cylinder for each of the starting heights, and then calculate the average velocity for each of the heights recorded in this column. Then use the average velocity to calculate the kinetic energy, 1/2 mv squared, and record that in that final right-hand column. And then you'll be able to graph and therefore compare our gravitational potential energy of our white cylinder at the top of the tube and the kinetic energy of our cylinder at the bottom of the tube. And you can have your prediction ready and then see what happens when you make your graph.